Hey everybody. All right, so I'm going to make a little video to help you out with your homework tonight. We definitely had some difficult problems involving scientific notation and real life science type problems. So here's the first one, something like this. Now I changed all the numbers in these problems, so I'll show you how to do them, but you're going to have to do them on your own with your own numbers. The speed of sound is approximately 1,234.8 kilometers per hour. A jet can fly at 2.9 times the speed of sound. Okay, so we need to find two things. Find the jet speed in kilometers per hour, and then we're going to take that and write it in scientific notation. So the calculation we'll be doing, get my thing out here. The calculation we'll be doing for A is we're going to be multiplying 1234.8 times 2.9. And I did say you could use a calculator for this, so we'll bring up our calculator. Times 2.9, and our answer is 3,580.92. Okay, so write that down. .92. Now, this needs to be in scientific notation, so I'm going to move the decimal point 1, 2, 3 places to the left, and that means that in scientific notation, this is going to be 3.58092. Now, remember, when you're doing scientific notation, you need to move the decimal point so it's behind the first non-zero number. Moved it 3 times, right? You dogs chill out. Every time I make a video, they start playing and getting all crazy because they hear me talking. All right, here we go. So that's the first part. That's the first part. And this is our answer. And the units are kilometers per hour. Okay, the next thing we need to do is we need to convert this into meters per second and write it in scientific notation. So we'll go ahead and take our 3.58092 times 10 to the third. We go that many kilometers in 1 hour, and we need to convert this. The first thing I'm going to do is I'm going to convert this to meters. And there are 1,000 meters in every 1 kilometer, so that's our conversion factor. When we multiply here, the units are going to cancel. My kilometers will cancel out, and I'll be left with meters. So I'm not going to do the full chain like I normally would by myself. I'll just do each step here. This is super easy because, look, this is 10 to the third. This is 10 to the third. We're really just multiplying 10 to the third times 10 to the third. So I keep the same number in scientific notation, 3.58092. 10 to the third times 10 to the third, by exponent rules, we know that that is 10 to the sixth. So basically, I'm just telling you how many meters there are in this many kilometers. We just multiplied by 1,000. Okay. The next thing we need to do is I'm going to think of this 1 hour. And you know what? I'm not going to do the conversion factor because I know sometimes it confuses you. I know that 1 hour is equal to 60 minutes, and that for every 1 minute, there are 60 seconds. So 60 times 60 gives me 3,600. In 1 hour, there are 3,600 seconds. So we'll take this number here, rewrite it. I wouldn't do all this by myself, but I'm just kind of trying to show you every step. To the sixth meters. And what I want to do here is I have meters over seconds. That's great. But what I really need to do is I need to have a 1. I need to have a unit rate. So I'm going to divide the top number by 3,600, and that'll give me my final answer. So here we go to our calculator. We're going to say 3.58092. Let's see, how do I do it here on this calculator? There's no E button. There's a 10 to this X, but I think if I press that, it'll take this times. Okay, that's how mine does it. So 10 to the 6 is a million. So I'm multiplying by 1,000,000 here. This number here is the top number of my fraction, okay? Not in scientific notation. So I'm going to divide this by 3,600, and that gives me a final answer of 994.7. So my final answer is going to be 994.7 meters per second. Scientific notation. Sorry, I need to do this in scientific notation. All right, here we go. Let's take this, move it over here a little bit. Move our decimal point 2 times. So this is going to be 9.947 times 10 to the 2 meters per second. Now, your problem is going to have different numbers. The key thing to do here is find the jet speed in kilometers per hour, convert your kilometers into meters. That was my first step. Realize that 1 hour is 3,600 seconds, so you make this fraction here. This is our rate. And then to make a unit rate, we always divide the numerator by the denominator, keep our units, and that's what I've done right here. Okay, that's it for the first problem. Let's go to the next one. The next problem says the equatorial radius of the Earth is 6,371 kilometers. A satellite orbits the Earth at an altitude of 175 kilometers. Find the distance the satellite travels in 100 orbits. I don't know if I spelled satellite, if it has 1 T or 2 T's. I guess it doesn't really matter at this point. I'm not the greatest speller. Anyway, equatorial radius of the Earth. Well, its radius of a sphere is just like the radius of a circle pretty much. So in our two-dimensional map, or our two-dimensional drawing, that means that the distance from the center of the Earth to the outside is going to be 6,371 kilometers. Now, the satellite is not on Earth. Okay, the satellite is 175 kilometers, so that would be this distance here. This distance here is 175 kilometers. And what we're interested in, first of all, before we can calculate anything else, is we need to find how far the satellite travels when it makes one orbit around the Earth. Okay, and that's going to be the circumference of this big black circle here. Okay, so what we're going to do, first of all, the radius of the black circle is going to be the radius of the smaller blue circle, and then this little distance here added together. So our radius of our circle is going to be, well, let's just figure out what that is. 6,371 plus 175, 6,546 kilometers. Okay, put this away for now. That's the radius. That is not our circumference, so let's find our circumference. If you can't remember this, most people think pi times diameter, and that's fine, but just remember that the diameter is twice the radius. So what we need to do is we are going to use this formula, 2 times pi times radius, and this will give us the circumference of the larger circle. Oops. Calculator. Where'd my calculator go? Here we go. Okay, so it's going to be 2 times, we'll use 3.14. That's fine. Times the radius, which is 6,546, which gives us a circumference of the black circle of 41108 point something. I couldn't see what it was. 0.88 kilometers. Now that's the distance that this satellite would travel in one orbit. Okay, that's the circumference of the black circle. The question we were asked was to find the distance the satellite travels in 100 orbits, and that's going to be 100 times this number, so I can just move in 100 orbits. The distance traveled is just going to be, well, times 100 is just moving the decimal point twice. So that's going to be 4,110,888 kilometers. But of course, since we just learned scientific notation, let's put this in scientific notation. And our final answer is going to be, let's see, 1, 2, 3, 4, 5, 6. So 4.110888 times 10 to the 6th kilometers. Okay, remember that every time we move the decimal place, that's a power of 10. This is a very large number, 4 million something, so we're going to have a positive exponent here. Okay, all there is for that one. Let's move on to the next one. The last one was something like this. I don't have the workbook in front of me, so I'm just kind of going on what I remember. I don't remember exactly what this last problem was. But it says the radius of an atom of cesium is 300 picometers. Okay, 300 picometers is an incredibly small distance. A picometer, and if you don't know, I think yours was a nanometer. In your problem, I do remember seeing nanometer. You need to find out what a nanometer is, okay? Or in this case, a picometer. A picometer, 1 picometer is 1 times 10 to the negative 12th of a meter. Pico means 10 to the negative 12th. Very, very small. So let's see. That means, let's see, 12 zeros. That's going to be 1 trillionth of a meter. 1 picometer is 1 trillionth of a meter. Very, very small. And somehow we need to convert this into centimeters. Okay, let's see how we do it. Let's start with this. Let's convert our picometers. So this is going to be 300. Instead of picometers, I'm just going to write 10 to the negative 12 meters. Okay. And let's see, 1 centimeter, and I need to find out, so this is the radius of 1 cesium. So it's going to look like this. We're going to have a cesium molecule like that, and then we're going to have another one like that, and they're all lined up. They're all lined up like this, end to end, and the entire distance that they form is going to be 1 centimeter. So we need to find out how many of these little guys stack up to make 1 centimeter. It's going to be huge. It's going to be a very large number. All right, so here's how we're going to do it. We're going to take everything and write everything in 1 unit. Now, 1 centimeter is equal to, it's 1/100th of a meter. So the way we could write that is by saying that 1 centimeter is 1 times 10 to the negative 2 meters. Or another way we could write that is 100 centimeters is equal to 1 meter. And we could divide this by 100 on both sides. So you get 1 centimeter is equal to 1/100th of a meter. Okay. And yeah, I think you can see now here that this is 10 to the negative 2. Okay, so that's why I'm using this here. The problem we want to set up is I'm going to take the total distance of this chain of cesium, which is going to be, so I'll go ahead and separate this off. This is where we're going to do our actual work down here. We're going to take the total distance and we're going to divide that by the radius, or not, let's use diameter. It says radius, so we're going to use diameter. The diameter is going to be twice this, or 600 picometers. So we're going to divide this by the diameter of a single cesium atom, and CS is cesium. Okay. Let's see, I think we might need it. If I put, let's say that 1 basketball has a radius of 6 inches. Okay, radius of 6 inches. So that means the diameter would be 1 foot. And if I asked you, well, how many basketballs would it take to line up end to end to make 12 feet? Well, we'd have to take the total distance, 12 feet, and divide it by the diameter of each basketball, which would be 1 foot. And that gives us 12 divided by 1 is, it would take 12 basketballs. Okay, so we're doing something very similar, but just with numbers that aren't as friendly. All right, so what we're doing is we're going to take 1 centimeter, but we're going to write it as 1 times 10 to the negative 2 meters. And then we're going to divide this by, this is the radius, by our diameter, which is going to be 600 times 10 to the negative 12th meters. The reason why we're doing this, we have to have our units be the same on the top and bottom so that they cancel out and we get a number. All right, so here we go. Okay, here we're going to apply some exponent rules. Okay, so this is going to be, let's see here, the 1 and the 600, I'm just going to leave it alone for right now, but 10 to the negative 2 divided by 10 to the negative 12, well, that's going to be 10 to the negative 2 minus negative 12, which is, my numerator is now going to have 1 times 10 to the 10th. And we're going to divide this by 600. And here's where you go to your calculator, if you need to. So here we go. 1 times 10 to the 10th is a 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. Divide this by 600, and there's your answer right there. To make 1 centimeter, it would take, let's see, how many of these? 16,666,666 molecules of cesium to form a chain 1 centimeter long. And then after that, we should take this and write it in scientific notation, which is going to be 1.6 times 10 to the 1, 2, 3, 4, 5, 6, 7th power. So 1.6 times 10 to the 7th atoms to form that chain. Okay, I hope this helped. If you have any questions, leave them in the comments. You can also check the section in the book where it talks about computation with scientific notation. That can help too, but I think that this should be enough to get you through these problems. All right, good luck.